My dear students, welcome to this class. In this class, we have to discuss the quotient group, also called as a factor group. Previous class, we discussed some problems related to the normal subgroup. So, let's start with the let G be a group and N is a normal subgroup of G. Now, the question is this: is there a natural generalization of the operation of a G that makes G by N a group? Now, what's the form of a G by N? That's the thing. So, G by N is nothing but is equal to, if we take N is a normal subgroup, and this G by N is nothing but is equal to the form of a An or Gn, where as the element of a this form. So, by a we can say that Na or G by N is simply is a either Na, or we can write is a An or G, left or right. So, by natural generalization, we mean defining a group structure like G by N such that G by N consists of a collection of that is G by N consists of a collection of all right cosets of N in G. We have a collection of all the right cosets of a N in G. We have a like this. So, we means a collection of a right coset. Similarly, we can define for G by N is a collection of a left coset simple. So, we have to just consist of a collection of all the right cosets of a G. So, now the question is this: how it is operation of a G makes G by N is a group into this form. So, as n is a normal in G, and each right coset of n is also the left coset of An. So, if n is a normal, then you know that the definition of a normal is say that the right and right coset is the same as the left coset. So, m is each right coset n is also the left coset. So, thus means we have to show that clearly G by N is the same as the An for any A belongs to the G. So, because we have N is a normal subgroup of a G, so by the normality we can say that G by N can be defined either Na or An, because we have a normal subgroup. By the normality of this we can simply use the left and right cosets are the same. So, define we have to for showing that is a group under this types of a collection of all the right cosets. So, first we have to define a operation on this case. Okay, what type of operation we have to this. So, we collection of all the right coset is this form. Actually, this meaning of this we have a Na binary operation, Nb is the same as a N of A operation B, like this. If we have a addition is there, we can say that if we have a Na plus Nb, then we can say that N of A plus B, like this. So, we just say that if we have we define this form. So, this is the form we have to define to this form. So, the problem is that the multiplication depend upon to the this clearly you say if we have defined a multiplication depend upon the A and B upon the representative of A and B, and we know that the cosets can have many different representatives. So, this coset have many different representation. So, we need to ensure our multiplication is well defined, and it is depends only upon the cosets concerned and not the choice of the representative of for the coset. So, this means we have to just say that we have to this we have to just say that this means we have to multiplication is what our this is ensure that this is we have to ensure that our multiplication is a well defined, means coset multiplication is a well defined. So, if we have a let N be a normal subgroup of a group G, let G by N be the set of all right cosets of a G. This means N of this we can write Gn G by n is equal to we have a in the form of a, we have to just say that n of A such that A is the element of a G. So we can say that G by n the set collection of all the right cosets of n in G, and we define the operation NA NB is equal to n of AB, and then we have to show that, try to show that G by n under this binary operation is a is a group. Now, first is we have to show that the operation is defined is a, for showing that it is a group. So that means first you ensure that the is a well-defined nest. So this operation we have to define, and first we have to check is the this operation defined by this is a well-defined or not. So let's we have to first we show that the above operation is a well-defined. So for well-defined nest we can try to take a two A1, B1 are the element of a G, and then NA is equal to NA1, NB is equal to NB1. Now we have to try to show that we can try to show that we have to A is equal to NA and B is equal to NB. So A is equal to NA and B for so N1, N2 belongs to the N. So this is clearly we have to write this NA is equal to NB and NB N is equal to A. This should imply that A is equal to some NA and this for some. So now we have to try to list. So AB, A1, B1 can be written in the form of a N1A because of we have a this A is the element of a G. So A can be written in the form N1A, B is the form of a N2B, and A1, B1 can be written as a N1A, N2B, and then you have a N1A, N2, N2 can be have from here we can say that from this B is the element of a G. So inverse of a this every element is equal to exist. So we can just write in the form of a this can be we have to write the A, N2 and B. We find the element of a B. B can be written as a form of a in the form of a this. Okay, so this is now by this we can say that this can be written as N A N2 A inverse and then A B, and then you can just say that this is the element of a since N is a normal. If N is a normal means N is you have a normal in G. So this means A is the element of a G. So A some element of N2, A inverse is also the element of N. So this is the element of a N, and if this is the element of N, this is also the element of N, and then this is the element of N since N is a normal, and this means this is also the element of N. This is whole the element of a N of AB. This can be written in the form of this form. So we can just say that this is we have to since N1 is equal to N, so this means N1 into this is also the element of N. Therefore N of A1 B1 is equal to written in the form of N of this is equal to AB, and then N of A1 B1 can be written as a this is the whole thing is the N. This is whole belongs to the N, and this is means this whole thing is again the N. Then this is clearly N. This whole is N of AB. Then we have to write in the form N of AB. A1 B1 is equal to N of AB. And now since we have a N1 A N2 A inverse, also we have a this N1 A N2 A inverse is the element of N. Hence we have a well-defined multiplication is there. So we have to just show that this is the element of N, and then we have to show that we're taking the N of A1 is equal to N of A, N of B1 is equal to N of B. So we have to N of A is equal to N of A1, N of B is equal to N of B1. We taking into this form. So and ultimately we have to show that this means this can be clearly is a for some N1 N2 this can be written in the form. So this is clearly is a well defined. So we have to show that clearly this map is defined is a this map we have to define is a well-defined map. Now we have to show that this is a group. That means we have to show that first this is a closed, and then we have to show that the associativity. So we have to first, as this is, if it is well defined, then automatically this is also a closeness. So we have to leave this. So it's a binary operation, so it's a closed, and then we have to try to show that this is associative. Take Na, Nb, Nc are the element of a three element of the gene. Then we have to try to show that N of A, N of B, N of C is the same as a N of A, then N of BC by this N of ABC. Now A, B, C are the element of a G. N is a normal subgroup, so this is means this is clearly this can be written as the form of a this can be written as a this can be written as a AB and you have C. This can be by the property, can be written as a N of AB, N of C. This can be written as a form of a NA and NB, and then you have a N of C. Now we have to show that Na, Nb, Nc is the element of a G by N. Then Na, Nb, Nc is the same as a Na, Nb, Nc. So this means we clearly by using this property, and then we have to saying that this is equal to both the right and coset, because the multiplication of a G is associative, so we can using this multiplication of a G is associative, so ABC is equal to ABC is in this form. Hence we have to show that Na NBC is equal to Na NBC. This is equal to this form. So clearly this map is well defined, and this collection of all right coset Na Nb is equal to Nab is well defined and also is associative. Now we have to check the existence of a identity, because E is the identity element of a group. So this N can be written as a N of E, and this is the element of a G by N. Now N of E is the element of a this, and we have to take N of A is the element of a G by N. Then we have to take a Na is equal to N of E of A. Now A is the element of a G, and E is the element of also the element of a G. Then A of E is equal to E of A, and this is nothing but is equal to N of A. Similarly, we can show that N of A, N of E is equal to N of AE, and this is the also is a N of A is there. So this means we can say simply that this N is the additive identity, N is the identity of a this G by N. So this G by N is a collection of all the right coset. Then inverse is also exists in this case. Identity is also exists in this case. Now we try to show that is the existence of a inverse or not. So we just take a E is the identity element of this group, N is equal to the identity Ne or N is the identity of a identity of G by N, and you have a Na is the element of a G by N, and then we have to say that Na is the G by N, A is the element of a G, then A inverse is also the element of a G. Then if A inverse also the element, Na is the element of a G, then Na is the element of a G by N, then N of A inverse is also the element of a G by N, and you have to know that the N is equal to Ne is the identity of this case. So if we take N of A inverse is equal to, by the definition, A inverse is equal to N of E, and this is equal to N. Similarly, A of A inverse, N of A is equal to N of A inverse A is equal to N of identity, and again N is equal to N. So means we have to show that G by N, the collection of this G by N is equal to, we take a collection of all the right cosets is the element of a G, form a group under the under the operation we have to, this is form a group under the operation we have to define into the form of a N of A. We have to define operation Na Nb is equal to N of AB. Under this binary operation of this collection of all the this cosets, right coset, and because I take n is a normal subgroup, so this is result is hold for the definition can be easily we can derive from the is true for a left cos as also. So this is clearly satisfy all the properties of a group is a closed, associative, existence of identity, existence of inverse. That means this is clearly we can say that G by N is a group under the operation we have to define into in this form. So this is clearly we have to show that this is a group, and then we have to so we have to just say that this is clearly is a group. Now we can define the quotient group. So let G be a group and N be a normal subgroup of a G. Then the group G by N consists of a cosets of N in G with the operation defined by this, or we can say that, or if we take a left collection of left cosets, an AB is equal to ABN, and is called the quotient group, or we can also call is a factor group of a this G by the normal subgroup N. So simply we can say that the collection whatever we have to collection of all the right cosets, and that is the consist of a G by N, and this G by N is clearly is form a group under this map defined. NA and B is equal to NAB. So we have to show that this satisfy all the properties of a group. So clearly this is a group. So we have to show that this is a group then, and this group is called is a quotient group, or sometimes also called is a factor group of a G by N. Now if a binary operation, if we take a G is an additive group, the N is a normal subgroup, then G by N collection is this form: N plus A plus N plus B is nothing but is equal to you have a N plus A plus B types. So is depend upon the, if you have a multiplication group, we have a defined into this form. If we have a group is additive, then we have to define into into this form. Now let's start with a very simple example of this. Just before the example, I just say that for a finite group G, the number of element in Gn is the just is index of n in G. So if we have to calculate the index of a Gn, and now index of a Gn, you can just say that simply is equal to order of a Gn is nothing but is equal to the index of a G by N, and is a normal subgroup. So we take a find the index of a this index of a this is nothing but is equal to, can say that order of a G upon order of N, and this is the index of a this. So this means order of a G by N is the same as a index of a G by N. So order of a G is the same as a index of a this by, so this means G by N is equal to G by N. So order of a this is equal to, you have a simply is equal to order of a G by order of N, and that is the order of the this quotient group, or we can call as a this is a factor group. So let's start with the one remark. If N is not a normal subgroup of G, then the operation defined in the theorem will not be well defined. So that means this is naturally question you can ask that we have to in the definition is also taking N is a normal subgroup, and then we have to define the collection of all the right cosets of this. We have to define in this form. We have a NA and B is equal to N of AB. My question is this: if N is not a normal subgroup, so then the operation defined in this theorem will be not well defined. Why? We just verify this. Suppose we consider a N is equal to G is equal to, we have to taking is a S3, and N is equal to generated by 1 2. There is a this is clearly is this N is a subgroup of a S3, and now since we have to take this 1 2 3 1 2 1 2 3 inverse, that is equal to 1 2 3, and clearly this you know that we have to prove that this is S3. N is not is the normal, N is not in a normal subgroup of S3 clearly, and now we have to try to this product. You can just check N of 1 2 3 is equal to N 1 2 and this is equal to this thing. Now n of 132 is equal to n of 13 is equal to this form. You can just verify easily. You can go n is equal to what? You have n is equal to identity and 1 2. Then you have to calculate n of 1 2 3. Then you have a we have a 1 2 3, and then you have a 1 2 and 1 2 3, and then 1 2 1 2 3 is equal to you have a 2 3. Similarly, n of 3, and we have to calculating the n of 1 3 2, and identity we have a clearly is equal to 1 3 2, and then we have a this is equal to 1 2 into 1 3, and that is equal to you have again is 1 3. So clearly we can say that this is equal to 1 3. So this means this is equal to 1 3 and 1 3 2, and then you can just check if you multiplied by this n of 1 2 3 and 1 3 2, and then this is not equal to n of 2 3 and n of 1 3. So this is not equal to n of 2 3. Now since n of 1 2 3 is 1 2 3 3 2 is equal to n, and this is not is equal to n of 2 3 is equal to into this form. So if we have a if we take a subgroup is a not a normal subgroup, then the binary operation we defined for this case for G by n is not a clearly is a well defined function in the case of n is a normal, not a normal subgroup. Okay, so now we have to a trivial example. Let G be a group, and we always G is also normal to itself, and identity also always is a. These are the two subgroups, and these are the trivial subgroups which are always is a normal into G. And if n is equal to G, there is only one coset in G that is equal to G itself, and this is the is a group of a one element, because we have to take a n is equal to G. So if n is equal to G is itself, the G by n is equal to nothing but is equal to you have a is only one element is equal to is a group of a one element, that is element is equal to G itself. Now second, we have a if n is equal to we have to take a 1, then ng is equal to you have a G for each G belongs to G, then G by n is the set of all singleton. So we have to just take a set of ng is equal to 1, 2, 3 and so on like this. So n is equal to 1, you have to multiply it by a, you getting a, multiplied by b, na like this. You have to write as a ng is equal to you have a G. So you have a suppose n1 is equal to you have a 1, and 2 is equal to you have a 2. So all the singleton elements. So you have a G by n is the set of all the singleton elements. So in this case, if G trivial normal subgroup is a G itself and G is equal to identity, if G is equal to n is equal to G we taking, then G is equal to only the one element in the group, and if we take G is equal to n is equal to identity, then all the singleton set of all the singleton of the collection of this G by n. Suppose we take a as 3. Now as n is equal to we take a 1 2 3, and then clearly n is a normal subgroup of this G, and then we can verify that easily n is a normal in G. You can take as you take generated by this 3. If you want, you can take a n of 1 2. If you want to n a 1 2, okay, just to verify n of 1 2 is equal to you have a 1 2, then you have a 1 2 3 1 2, then you have a 1 3 2 1 2, and then this is nothing but is equal to, you can just check, you have a 1 2. So we just multiplied by this, and then this equal to the same as equal to we have a 1 2 n is also the same. So this case clearly you can just say that this example. So this means we have a only there is a for this is a you have a only possibles are the G by n is a, this only two sets are there, n and you have a n 1 2, because if you have a taking this elements of this, you getting the n 1 2 is all. That means all are the this is repeating into this form. So by this we can show that G by n is nothing but is equal to the elements of n or g by n. G by n means g by n is nothing but equal to, we have a collection of all the right or left cosets. A is the element of a G. A is the element of a, you have a S. Then you have to collection of all the right cosets. There is only two possible cosets are there. One is n, another is a n 1 2 for this n is equal to generated by this subgroup. So we can just check. Now we have to take another example. Like G is equal to U20, then there is an element of this, and n is a subgroup generated by 1 and 90. If you can easily check that, this is a clearly is a n is a normal in G, n is normal in G, n is normal in G. You take a 3, and then you take a n, and you take a 3 inverse is again the element of a one of the element of a 9, because you take a inverse of a 3 by just you getting the identity where you have a 7 and 3 are the inverse of each other, because 7 to 21 divided by this, so 7 and 3 are the inverse this means you have n, and this is equal to 7, and this is equal to, if you take a you have a 3, and you have a 3 into 19, and then you have to write the is equal to, you have a 3, you have a 19 into 3 into 7 1, so again you have a 19, so this means is giving you have a like into the 3 into 7, and this is equal to 1 and 19, and this is the clearly this is containing into the this is belongs to the n, and this is the same as equal to n. So you can take a 3 and 7 is the n, and then clearly you can verify all the elements we have to in this form. So this is clearly we can say that in this form, this we can simply say that this n is a clearly normal in G. Now we have to find the what type normality, because G is abelian, so there is a left cosets are the same as the right coset. So this means this is not very difficult to finding for any abelian group is also is a, if a group is abelian, then this is clearly the normal. So now n1 is equal to, we have a 19, n3 is equal to 3 and 17, n7 is equal to, we have a this, n9 is equal to, we have 9 and 11. So we have to calculate n1 3 7 9, and now we have to this is only the G by n is equal to, we have a n1 n3 n7 and 9, and these are the collection of this, because all other the repeating are there. So the complete table of a group table is given in table point 1. We can also use this table to find the inverse of a this because n3 and 7 is equal to, we have a n1, and since n1 is the identity, so this means n3 inverse is equal to, you have a n7. So by this can be describe you by the this all this thing we have to describe by this table. Now this table you can just say that we have to taking this form n3 and 7. Now we have a n3 composition and 7, so we have a this is equal to n1, and now you just say that is equal to n1. So if n1 is the identity element, here the identity element is equal to n1 because n1 is equal to, you have a 1 into 19, and you know that we have to know that identity is equal to same as n is equal to this 119. So we can say that n1 is equal to 119. This means n1 is the identity element. So we can say that n1 is the identity element, and then n3 and n7 are the inverse of each other. Now n7 and 3 this is inverse, and 9 is the inverse of itself. So this means if you take we take a collection of a G by n is only these are the elements n1 n3 n7 and 9, because they say that a collection of all the right or left coset. And now you just check how many cosets are there. So this is 1 2 3 4 5 6 7 8. So you have know that the order of a G is equal to 8. Now order of n is equal to, you have a 2, then you take a index of these 2 is equal to 8 by 2 is equal to 4. So there are 4 different cosets are there, left or right. So these are the 4 left or right cosets are there. So in this collection we have only the possibility of these 4 collections are there. So this means there is only possibility G by n are these 4 elements. N1 is the identity element. Now you can easily show that N1, N3, N7, N9, and then you see is we can show every element is we just say that this is the identity element, and then this is the identity element, this is the identity element, this is the identity element, and this is the clearly this table is closed. And also inverse, if we find the inverse of a n1 is equal to its identity element is always to inverse itself. And now we have a 3 and 7 are the inverse each other, and 9 is the inverse of again itself. So we can simply say that by this table we easily show that this U20 factor group of this U20 over 19 normal subgroup generated by 19, and then this table easily show that means we have a this by the table we can also identify all the possibilities. So this is clearly is a group, and then we have to show that this satisfy all the properties of a group. So we clearly this is a important we have to discussion in the quotient group. So this is also called as a factor group. So today I stop to the lecture here, and we have to continue in the next class for this quotient group. And so thank you very much.